Let's solve this problem. It asks for the reactions on the bent rod, which is supported by a smooth surface at B and a collar at A, which is fixed to the rod and is free to slide over the fixed inclined rod. That's a lot of words. So you have to look at it. What is this bent rod that they're talking about? What color is it? Gold color? Sure. Yeah, that's that gold color bent rod. It extends from right here down. Okay. It's supported by a smooth surface at B. Well, this surface at B, we're not, in a future chapter, we'll handle friction basically on surfaces, contact friction. But at this point, our surfaces are smooth. So the only type of reaction between the rod that contacts at point B and that smooth supporting surface would be a normal force, normal to that surface, non-tangential. That'll be a friction force. That's later, not this chapter. All right, then we have a collar at A. What do they mean by a collar? Well, it's shown right here. So that collar could move up and down along this other rod, okay, and it can freely slide over that fixed inclined rod. That's what the collar can do. Maybe we need to think about each of those boundary conditions, like I just talked about, this smooth contact. But with this collar, if somebody just forgot the rest of this and said, I'm going to take this and pull it down, would it go down freely? Sure. So think about this. If I said, I'm going to pull it this way, away from this inclined rod, which is blue, okay, would it allow it to be pulled away from it, perpendicular to it? No, it wouldn't. And so it's smooth, and so it can slide along the axis of this inclined rod, but not perpendicular or normal to it. Okay. Now the other thing is with this collar, if I grab this end and I sort of tried to twist it up, not pull it out or slide it down the rod, but just twist it and pivot around point A, which is right in the middle, would that be freely, easily done? No. That collar would say, sorry, I'm going to support it to stay in the rigid position that is in. And it would develop a non-zero moment at that point to react to the intended, because if you grabbed it out here and started lifting up, it would want to make it rotate, but we are not having motion in this class. That's the next class, dynamics with acceleration. So it would basically develop a reaction, a non-zero moment reaction at A, to hold it in place, to not allow it to rotate up. How about if you grabbed it over here and you grabbed it and tried to force it down? Well, it would develop a non-zero reaction moment at A in the counterclockwise on my object. Just like, go back to forces. If you said, I'm going to grab it and try and pull it out this way, well, it would develop a reaction force at A that would hold it back. Okay, well, let's say I don't try and grab it and pull it out, but I'm trying to push it in. Well, the reaction force would change direction. It would be pushing up to support it. All right, so hopefully we understand every time you encounter new contacts or supports, try to really understand it. So it's not just rote math and repeating itself. So what are the things that we're asked to solve for? Maybe introduce symbols for them. Oh, I think I'm asked to solve for the tension in the cable A to B. That's what I mean by what are we trying to solve? And then what would be the units for what we're trying to solve? How many of those are there for this problem? How many unknowns are there? What are they? And what are the anticipated units? What symbols would I have for them? Before we jump into Or maybe you start doing that at the same time as getting a clean free body diagram, but don't solve it yet. Okay, so I'm going to pause. You need to do that. You need to know, what am I looking for? What symbols am I going to use to describe the unknowns that I'm solving for? What are the anticipated units of those? And what's my free body diagram for this problem? What's the appropriate free body diagram for this problem? All right. This is the hardest thing to do, right? I'm going to be working on a free body diagram. You have to come in here and cut through the supports for the collar. And then you have to come over here and cut the object, which is the bent rod is the focus of the study, free from the surroundings. It'll include the load. It'll include this moment load, a force load. It'll include this moment load. And then I have to come down here and you try and redraw it. So it comes like this. And we'll go ahead and put back our load of F and moment. And down here, I'm going to have a supporting normal force at B. And because this surface right here is a 12, 5, 13, that's a similar triangle showing the angle. And some people converted it to a degree angle slope. You can do that. But you can also come in here and say, if that's a 5 rise on a similar triangle, basically I'm going to take that triangle and flip it such that it'll be a 5 horizontal. And instead of being a 12 horizontal, the normal to it will be a 12 rise. And a 5, 12, you square the 5, you square the 12, you add them together, you take the square root, you get 13. That's just like a 3, 4, 5 triangle. It's a 5, 12, 13 triangle because it's perpendicular. This is perpendicular to the normal surface. So that's one unknown. So up here I use this as an example. There's no tension in this problem. We're going to be looking for n sub b as one unknown in units of pound, because that's the normal reaction at B. All right. Then we come over here to this collar. That's the most complicated. And it's going to have a normal at A. It's going to be perpendicular to the axis of which that collar can slide. Okay, so normal at A, maybe I come over here and draw that. The normal at A, the normal at A. I think it's good to draw it both on your sketch that's given and then on a separate cutaway that's actually taking the surroundings and throwing them away and hiding them. And it's really a clean free body diagram. All right, and then it's units of pound. That's one unknown. In the direction or orientation of that, we should be able to figure out from this 1, 2. It's not a 1, 2, 3, is it? It's a 1, 2, what? You are so good. Didn't we say we're going to be experts at right triangles? Remember that? Yeah, we are experts at right triangles. We could do the tan, arctan. We can do the rotation, the sine, the cosine. We can do Pythagorean theorem day and night. So it's a 1, 2 square root of 5 triangle. Maybe we don't like the square root of 5, but there it is. All right. And so when we come over here, if we wanted to, we could say instead of going horizontal in the 1, it would be a vertical in the 1. Instead of a vertical in the 2, it'll be a horizontal in the 2. And that probably doesn't look so good, does it? Maybe back this force up a little bit more. It would be a 1, 2 square root of 5, and the magnitude of this n sub b, maybe I draw it down here a little cleaner, a 1, 2 square root of 5. You see that? That'll help me pick off the x component and the y component. Some people are getting ahead of themselves a little bit. They're saying, I need to do some of the forces in the x. And so I'm going to need to pick off this component. But as soon as they put an additional force vector in there for the component of that n sub b or n sub a, it starts to be confused. It looks confusing. And students can easily get confused, so we want to just have a kind of clean, similar triangle to help us get the two components when we need them.
So when you look to the summation of f of x right to y, you use the second triangle because if you use the little first one, it'll give you a different number, right?
These are the same. Did I draw them different? This is 1, 2.
Because on the one that give you x is 1, and then
this is to give the orientation of that rod. That's the information given. And
then you change it to the other one. So you use the second one, right?
yeah, definitely the second one, because it's giving me the orientation of this normal reaction force, not normal B, it's normal at A, yes, normal at A. And then the last, that collar, will develop a non-zero moment. Now, I can't tell by looking at this problem whether or not it'll be this way or that way. I just need to pick one. And so I'll pick that it's going to be a non-zero moment that would make it tend to rotate, if that was the only thing applied to my object, in the clockwise direction. Just like I picked a direction for n sub b, didn't I? The direction, I'm sorry, n sub a. The direction for n sub b is pretty simple because that smooth surface can only push up on the rod. It cannot, if the rod wants to fly off the smooth surface has no glue to hold it there. The rod will just fly off. So the problem, if it's well posed, n sub b has to be greater than 0 as shown. It cannot. It's impossible to be negative. It doesn't make any sense. That doesn't mean that in the textbook or in a problem, that there's sometimes a problem that doesn't make sense. It's just in the rush of things work out such that it doesn't make sense. For example, if somebody took and they wanted to change this up, they put a large moment this way, right here. And they said, no, not 380 pound-foot. Let's put 38,000 foot-pound. I'm telling you, I could predict that rod's going to come off of that surface. You know what I mean? It's not going to be a good static equilibrium problem. You can just envision how to mess up a poor problem. Okay, so I'm going to be looking for the moment reaction at A. In the units for that would be foot-pounds, or as the book likes to switch it. I think the book changed. I don't know what version of the book has changed it, but it was always foot-pounds, and now it's a pound-foot, which is a tongue twister for me. All right. You ready? You've got a clean free body diagram. You clearly know what are your unknowns. You might as well do a count. This is a 2D problem. If you have more than 3 unknowns, you're going to need more than 3 equations. What are our traditional number of equations in 2-dimensional equilibrium problems? 3. Sum of the forces x, sum of the forces y, sum of the moments about any point. That's it. That's the common traditional. Okay, so if you get more than 3 unknowns, you're going to be lost. Yes?
Yeah, so we assume that the clockwise direction is a positive direction. Are we assuming that the clockwise direction is a positive direction?
Yeah, whenever you put a free body diagram, the direction of your reactions is very important. And so one student over here on their free body diagram could have said, I think it's going to have a clockwise orientation for m sub a. Another student could have put, I think it's going to be the opposite direction. I think it'll be counterclockwise. When you grade that problem, you have to pay attention because the answer has to match with their free body diagram. The free body diagram is part of the answer. Yeah. Yep. Just like some student here said, I think it's going to be pulling in this direction. Well, if actually it's not pulling in that direction, but actually pushing in the opposite, their answer will be negative. And it would be graded correctly. There's nothing wrong with having an assumption it's the wrong direction and then calculating a negative answer. Okay. We have it now. You ready to try and solve this problem? How would you solve it for one or two or three of the unknowns? Should I give you a minute, or do you want me to move forward? Because we're already at 9:30. I got 20 minutes left. I'm not going to be able to solve the other problem. Just watch me solve it? Traditional lecture? All right. Well, if I look at this problem, I like, after you've solved a few of these, your go-to equation for the first equation is do the sum of the moments about some point. And if you can pick that point judiciously that cancels two of the forces, great. All right, I have this force, its line of action, this force with its line of action. If I do the sum of the moments about the point of intersection of those two lines of action, then I can get one equation, one unknown, and I will be able to solve for m sub a. Too complicated. Too complicated for this problem. Back up. That strategy, which works for a lot of problems, after you solve at least 10 problems like this in 2D, you'll know what I'm talking about. I'm looking at a lot of blank stares, which means you need to solve some more problems. Okay? But I'm telling you the strategy here. Okay, now, once I sort of figure out my go-to equation of some moments about some point, either on the body or off the body, it doesn't matter, is not going to give me one equation, one unknown. I'm kind of stuck with at least a minimum of two equations with two unknowns. I don't like it, but that's the reality of the math. Okay, so I'm going to go with the sum of the forces in the x equal to 0. What does that give me for an equation? I'm going to get rid of this out of here. What does that give me for an computer is acting up again. All right, this is 150 pounds. This was a 380 pound-foot moment applied. Okay, so some of the forces in the x give me, what I have to do is do you want to run with n sub a in this direction or not? I need to pick it on and put it on my free body diagram, and then don't change it. That's another recommendation. Once you get your free body diagram and you pick the direction for each of the forces and each of the moments, if you have reacting moments like this problem, don't change it, even if you realize, oh, it's negative. It'll only create more problems and confusion for you. It's more difficult to do it. Just pick it and leave it. So can I pick n sub a in that direction and leave it, or should I swap it? Swap it. Okay, swap it. Because that's a key thing. Don't be changing it. All right, there's n sub a. Now, so what I have to do is I come in here and I say n sub a times which component? Isn't it 2 over the square root of 5? Isn't that in my positive x direction? Okay. Now come over here to this n sub b. It's in the negative direction. I own that negative sign. I have to put it in my equation. I can tell it's in the negative x direction. And it's going to be n sub b, and then I have to pick off that component. Isn't it 5/13? Hey, we're experts at forces, aren't we? And there's nothing else. Nothing else in this whole problem. Now let's do the sum of the forces in the y. Sum of the forces in the y equals 0. What gives us that? So we pick off the n sub a. We're going to this time pick off 1 over the square root of 5. And it's in the positive y direction. I'm going to have 150 pounds from this load applied. That's in the negative y direction. And then in the positive y, n sub b times 12 divided by 13, and I paused and I looked, do I have anything else in the y direction for the sum of the forces in the y? No, I don't. So at this point, I look and I say to myself, I have two equations with two unknowns. I tried to get one equation with one unknown. I'm going to have to settle for two equations and two unknowns. And now you need to solve for those. And so if you solve for them, you're going to get that n sub b turns out to be 2 divided by the square root of 5 times, well, no, let me do this. Let me just give you the final answer. If this would erase, all right. N sub b is going to come in at 125.8 pounds, and n sub a is equal to 54.1 pound. You're going to have to be able to solve two equations, two unknowns. Right? Correctly? Okay. Now that I've solved for those, I need one more equation to solve for the m sub a, that reaction moment. These are done. I need m sub a. So, it's your choice. Anybody want to suggest a place to do the sum of the moments about? About point B? You could definitely do it about point B. Okay. Point A, you could do it about point A. Those seem to be the most logical places, either point A or point B. I don't see an advantage of either one. Because if you do it at A, you have two components of the normal reaction at B that have to be considered. If you do it at B, you have the two components of the normal A that have to be considered. So let me do this. Let me move up here and try and get it in here. I'm going to do the sum of the moments around point A, that must equal to 0. I know this notation can be a little confusing. It's like, this is an equation. I'm writing the sum of the moments about point A, and one of the first things I have to write is the moment reaction at A. And if you like, you could put an arrow like this and say, it's clockwise. That's the direction it wants to rotate. See? Because I'm going to worry about my plus and minus. Some of these things are going to make it want to rotate counterclockwise, and I could be off by a sign. Yes, sir?
You're saying the reaction moment is
Yeah.
clockwise?
Well, that's my assumed, as I've shown it in the free body diagram. If you chose a different direction, then your equation would have it consistent.
I
Yeah.
was thinking about that earlier, but
Yeah.
I was going to ask why did you use the actual moment? So I figured like the actual moment basically was 150 pounds was going to be clockwise and the reaction counterclockwise.
Yeah.
That's not bad.
Let's just work the math. Okay. Then we're going to have this 150 pound with a moment arm distance of 3 foot. And which way does it want to rotate? Around point A, clockwise. We have the 380 foot-pound. It's sitting out here. It looks like it's applied at this nameless point at the bend. And which way does it make the object want to rotate? Clockwise. And then we're going to decompose this normal at B into this is a 5, 12, 13 triangle that we've used before. And so it'll have, let's do the 5, 13th, n sub B. That's going to be pushing in the negative x direction. It has a moment arm distance of 2 foot, and it makes it want to rotate not in the clockwise, but in the counterclockwise. So I'm going to put a negative sign because it's like this. We've done this before. It's like that's the direction it makes it want to rotate. No, I'm sorry, that one is correct. It's in the clockwise, right? The other one, which is up, which is my 12 13ths n sub B with the moment arm distance of 6 foot. Come on. Boy, this computer is doing something crazy. 6 foot. That one makes it want to rotate in the counterclockwise. So what I'll do is I'll put a negative sign here, and it's now correct in the sense of it's not contributing a positive clockwise, but a negative clockwise. And I pause and I look at it. Is that everything in this, or did I miss a component? So the x component, the y component, I have the right direction. I have one equation, one unknown. I solve for m sub a from this equation, and it's negative 230 foot-pound. So don't go change your free body diagram just because you calculated a negative answer. Leave it alone. And that negative says my intuition or my first guess was wrong. It's actually in the opposite direction. No big deal. Okay? Very good.